So that sort of problem we're going to see in polar graphs is finding the area bounded by multiple polar curves. So that's going to be similar to what we've done in rectangular form when we have multiple graphs, but there are a few variations that we need to be aware of. So let's start off with this example. We've got R1 equals 1 minus 2 cosine theta. So if I'm going to graph that one, I guess I'll graph that one in blue. Starting with theta equals 0, we get 1 minus 2, which is negative 1. So that's going to be this point right here. As theta increases to pi over 2, r is going to increase to positive 1. So if r goes from negative 1 to positive 1, it's going to have to pass through r equals 0. So it's got to pass through the pole at some point. So it's going to do some sort of graph like this. Okay. We could spend a little bit more time setting this equal to 0 and figuring out that theta equals pi over 3 is going to be the theta value that causes r to equal 0, which is going to tell us that this radial line right here is the tangent line. Looks like I did a pretty good job of that, so I think I'll leave it as is. Anyway, so as theta continues to increase from pi over 2 to pi, r is going to increase from 1 to 3. So we're going to end up out here, and this is going to be like a continually increasing value of r, right? Starting at 1, getting bigger to 2, getting bigger to 3. And then it's just going to do the same mirror image on the bottom half. This is going to be an inner loop limacon. So we're going to go around like this. And it's going to look something like this. All right, so there's my attempt at an inner loop limacon. It's not perfect, but perhaps it's good enough. R1 or R sub 2 equals 1. That's simply a circle with a constant r value of 1. All right. So we've got two polar curves. And then the question is, can we find the points of intersection of the graphs of the equations? We're going to start by sketching, which I just did. And now we're going to see if we can read the graph. And it sure does look like we've got 1, 2, 3 different points of intersection. These are 1 comma pi over 2, 1 comma pi, and 1 comma 3 pi over 2. I'm convinced. Okay, let's see if our algebra supports that. If we set R1 equal to R2, if we set R1 equal to R2, then we get 1 minus 2 cosine theta equals 1. And we're asking what theta values cause these r values to be the same. So if we subtract 1 from both sides and divide by 2, negative 2, we get theta equals pi over 2 and 3 pi over 2, but not pi. So I'm getting this one and I'm getting that one, but I'm not getting this one. So the algebra might not tell the whole story. So what's going on here? Because there are multiple polar coordinate pairs that correspond to the same location on the polar plane, this algebra is not sufficient. We also have to consider a few other possibilities. Remember that this first value that I tried out here was when theta equals 0, and I got an r value of negative 1. That's not the same numbers as 1 comma pi, but it's the same location as 1 comma pi. So we're seeing that perhaps R1 equals negative R2 for theta values that differ by pi. So for example, R equals 1 when theta equals pi for the red circle, but R equals negative 1 for, wait, I'm saying that backwards, aren't I? Anyway, it's basically the idea is that we're hitting the same point, but using different theta values to get there. Okay. The other way that we might end up seeing R1 equals to R2 failing us is that if the two graphs intersect at the pole, because that way the theta value doesn't matter. If r is equal to 0, then we're always at the pole. Now, on this one, that was irrelevant because the red circle didn't actually go through the pole. But that's another point to consider. All right, so we're going to try this one. This is going to be another intersection problem. But this time I'd like to start algebraically and then see if we can verify with the graphs. So definitely start off with R1 equals R2. R1 equals R2, so 1 minus cosine of theta equals -3 cosine of theta. And if we try to solve for theta, we can, I don't know, maybe I'll add 3 cosine theta to the left side and subtract 1 from the right side, so get cosine of theta equals -1/2. That's a 1/2. Let's try that again. And that means that theta is going to equal the theta values that when you take the cosine, you get -1/2. That's what, 2 pi over 3, 4 pi over 3. Cool. So looks like we've got 2 pi over 3 for the theta value is going to give us 3/2 for the r value. And I think the same thing for 4 pi over 3. We're going to get 3/2, comma, 4 pi over 3 is another point of intersection. We can double check that because both of those equations give us an r value of 3 over 2 when theta equals either 2 pi over 3 or 4 pi over 3. All right, so that's good. What about the pole? Pole, question mark. Do these two curves cross the pole? So let's double check. R1 equals 0. So that's 1 minus cosine of theta equals 0, or cosine of theta equals 1, or theta equals pi over 2 and 3 pi over 2. So yes. And then what about R2 equals 0? Well, that's 0, well, I'll keep it on the same side of the equal sign. -3 cosine of theta equals 0. Okay, so that means that cosine of theta equals 0, or theta equals, wait a second, hold on. This is pi over, I made a mistake. I'm not thinking straight. You guys are screaming at the computer. Sorry. I was not thinking. The angle whose cosine is 1 is 0. All right. So it still crosses through the pole, right? R1 crosses through the pole. R2, yes, also crosses through the pole. I don't care that these guys are different. I care that they both exist. The idea is that they're crossing the pole at different points in time, but they definitely do touch there. So they're forming an intersection point right there. So we have also the pole. All right, so be on the lookout for that. So we can verify this graphically. We'll start with 1 minus cosine of theta, which is going to be a cardioid, I believe. Our r value starts at 0 and goes up to 2, and then goes back down to 0. So that's R1 in green. And R2, D2, in red is going to be a circle that goes to the left, altitude 3. So we can see that there are, in fact, 3 points of intersection. The 2 that we found by setting R1 equal to R2, which is theta equals 2 pi over 3, and theta equals 4 pi over 3. But also we get this other one at the pole, because they both touch the pole just at different points in time, or different theta values if you want to think about it that way. Alrighty, cool. So that's a quick little review of some pre-calculus polar graphs. We need to be aware of those extra pieces of intersection possibilities, possibility 1 and possibility 2, so that when we are trying to find the proper theta values to integrate, when we start finding the areas, we will put the correct bounds in our integrals. So that's what's coming up.